think for people in India, dinner is waiting. For people in Europe, lunch is waiting. So the final presentation, and that's also an important topic as we've learned already from several other presentations, is about metallization, which is really one of the key issues, challenges, opportunities for TOPCon. And we have with us today Dr. Guo, who's the CTO at Solamet Electronic Materials. Some of you probably remember the name Solamet as a product name. Dr. Guo will also probably shine some light on what it is about the company name when he talks about the technical challenges and solutions for metallization of high efficiency N-TOPCon solar cells. The floor is yours.
Okay, can you hear me?
Yes.
Great, let me share my charts really quick. Okay, can you see my charts?
Yeah, perfect.
Okay, great. Thank you, Michael, for the kind introduction. It's a great honor today to participate in this forum. So today I'm going to talk about, as Michael alluded to, there are a lot of challenges that's still facing for the metallization. And today I'm going to kind of give a talk on, going to talk about the challenges as well as the solutions for metallization. I hope this will bring excite everyone, and then hopefully open up some collaborations. Hold on. It's not okay. So the agenda for today. So I will first give a brief introduction to Solamet Electronic Materials. So as Michael mentioned earlier, this Solamet, the company, may be new to some folks, but the brand Solamet, has been a legacy in the PV industry. So I'm going to give a quick introduction, and then I will jump right into today's topics: the metallization needs for high efficiency TOPCon. And for that, there are three main topics I would like to cover. First, it will be on the progress on the finite screen printing. I think that's very relevant for today's topic, especially in terms of the high efficiency and lower cost for a N-TOPCon metallization. And then from the more of a technical perspective, a dive on the current limitations on the metalizations, as well as some of the solutions and approaches that we are seeing from the metallization perspective in terms of how to improve on the efficiency for N-TOPCon. And then I will also do a little brainstorming or quick discussion on the next generation that we see that's on the horizon. That's right after that's building on the TOPCon technology, which is the TOPCon back contact. I think that's also an exciting next chapter for TOPCon. Okay, so here is a quick introduction to Solamet Electronic Materials. So Solamet, it's previously we know as the DuPont Solamet as a brand for the DuPont PV Solamet PV metallization products. And some of you may have known the Solamet back in this year, July 2021, a investment consortium from China, Jiangsu Shuote Electronic Materials, has successfully fully acquired the entirety of the DuPont Solamet PV paste business. So that includes all of its people, the manufacturing plant, the R&D facilities, as well as all of its IP portfolios. And Solamet's very proud of its contribution to the industry for the past 30 years, and we have built a very strong IP portfolio on the metallization technologies. And the Jiangsu Shuote, the consortium, it's led by a investment firm, so mainly Haitong M&A Capital, as well as including some other well-involved interest, the investment interest firms in the PV, as well as some experienced strategic investors. So we have a very strong backing both on the capital as well as in terms of the on the board. And then the name was officially changed to Solamet Electronic Materials to carry on the legacy of Solamet in 2021. And so as mentioned previously, so the Solamet, we've maintained our global layout as previously known in the DuPont. So our headquarters is currently now in Taizhou, China, but we maintain our operation center in Shanghai. And then we still have maintained 2 R&D facilities, one in Shanghai and one in Taiwan, as well as all the R&D personnel from the US that were originally in the Solamet business. Our manufacturing plant is still maintained in Dongguan. So internal overall operation, it's an independently self-run business. And we are very excited to enter the new chapter and hopefully to contribute to the PV industry. Okay, so a little brief history of the Solamet, especially in the past 10 years. I think it's also very relevant to today's topic in terms of the metallization for the new cell technologies. So Solamet has been in the PV industry for 30+ years, and we have consistently been in the leader in terms of innovations on PV technologies for the difference in terms of continuously improving the solar cell efficiency as well as reducing costs. And so just kind of like to name some of the few very key innovations from the Solamet in the past decade, right? So I think many of you are probably aware of a leap in the metallization technology for the P-type, which is the innovation made by Solamet in terms of the lead tellurium oxide, the glass-free chemistry that revolutionized the PERC technology. A key milestone was enabling the LDE technology, and now this technology has been carried toward the current PERC and PERC-SC. And in terms of the advanced cell technologies, we have also continuously been investing in innovations in the Solamet business in terms of enabling technology for the advanced cell architectures. So example shown here is IBC technologies that we developed as a novel approach using a one-page solution to contact both a screen printable metallization to contact both the N and P-type metallizations for IBC, as well as a very early look into the N-PERC technology, developing the total package solutions to enable the mass production of N-PERC. I think both of these are very relevant now as we are really getting into the cusp of the emergence of the N-type high temperature fire-through technologies like N-TOPCon as well as TOPCon back contact. And along the line, a very important trend for the metallization is the continuous drive to finer lines, and Solamet has always been a pace setter in terms of advancing the finite technology. And so far, for like the P-type, we're able to push the limit to screen printable technology, printing technology to 15 micron screen openings, and we are continuously pushing the limits on that. And I think that the finite technology is going to be a key player in terms of reducing the metallization cost for the N-TOPCon as well. Okay, so the speakers before me previously have already talked a lot about the industry trend as well as the technology trends for the silicon solar cells. So I just kind of here do a quick highlight in terms of from the metallization screen printable metallization perspective. We think that there is still a lot of opportunities that remains for both the P-type and for the N-type. For the P-type, the current mainstream is the PERC technology, and there is still a continuous incremental improvements in terms of the technology from the refinements of the processing technology, and we are still seeing a continuous increase in the efficiency especially in the past couple of years, and that also plays a role in terms of putting a more of a challenge on the N-TOPCon, because for the N-TOPCon to deliver its cost effectiveness as well as the internal LCOE, it needs to have demonstrate both internal processing cost wise as well as efficiency over the PERC-SC. But I think with the exciting technology we heard today, I think the 2022 will be a very exciting year, a breakout year for the N-TOPCon. And so along the same line, the HAT, which had already been covered by this forum yesterday, so I'm not going to talk a lot about it, but for the HAT, we're also seeing some very exciting developments. So I think we are at a very exciting time of the emerging of new cell technologies. And personally here, I'm more coming from a screen printing background, as well as the high temperature firing. So I think the N-TOPCon itself also offers a lot more opportunities in the shorter term. So we are seeing, the maturization of the N-TOPCon technology, as the speakers before me just talked about, and we also see in the near term, there's also it's a very nice platform to build on, which can then be extended to like a TOPCon back contact, which can further improve the cost structure for the N-type TOPCon technology. So I think it's going to be a very exciting time for both in terms of the self-engineering side as well as from the metallization perspective. Okay, so the speakers also, before me has discussed a lot about the challenges, the opportunities for N-TOPCon. So over here, I'm kind of more focused on the metallization part. So, as mentioned, by everyone, I think, as well as the everyone during today's forum, the main issues, the main challenge for the any high efficiency cell technology is basically, the benchmark is the P-type PERC, right? So the first thing is you have to be able to demonstrate a very good efficiency premium against the P-type PERC, right? And then as well as it has to be cost effective in terms of manufacturing, especially considering PERC technology. The manufacturing process has been very well refined, and then it's at a very cost efficient. And so one of the challenges in terms of solar cell manufacturing is in the metallization. So if we take those two main objectives, which is in terms of efficiency and the cost effectiveness, then if we transfer it to metallization needs, and I kind of have it narrowed down to 4 main points, right? The first is basically how to continuously improve the cell efficiency, especially for N-TOPCon. There's still a lot headroom in terms of efficiency improvements. So how do we develop the metallization technologies to realize those efficiency headroom? And then another thing that has been mentioned a few times is how to reduce the silver consumption. That is one of the major costs in terms of the solar cell manufacturing. And other things that have not been mentioned a lot, but I think it's also very important for the metallization, is to improve the overall cost of ownership. It has to be able to enable higher throughput. So that's the beauty of screen printing, because of its a very mature technology, and it can be done at a very high throughput. So I think overall, screen printing is still going to be a dominant technology for the next few years to come. And another thing is how to improve production yield. And I think some of the speakers mentioned before about some of the issues that still currently being facing the TOPCon cell processing, for example, like the polysilicon wraparound, the passivation wraparound. So how do we design metallization solutions that has wider processing windows that, it can also improve to ensure that we have a high production yield. So internal metallization, those are some of the key challenges I think they are still facing internal for the N-TOPCon. And if we translate that to PACE opportunities, right? So I think I kind of separate out into the, as I mentioned briefly, from the TOPCon, we need a silver PACE for both the front side and the back side. And then, so I kind of separate the challenges internal out to the front and back. For the front side, it's a facing the sun. So obviously it's how to enable the finite printing. I think there's a lot of learnings we can leverage from the P-type, but also, of course, there are also challenges that are still there for how to adopt those finite printing technology from the P-type. And then a big topic is on the recombination and as well as the contact performance of the aluminum silver paste. And I will also discuss a little bit more in the later slides on some of the technical challenges there and then some of the opportunities that we see. And another very important aspect of it is for the front side is how to enable higher efficiency architectures, right? So like, for example, a lower higher R-shaped emitter or a selected emitter design for the front side, or a more optimized AR coating that can offer a better light trapping, or can offer less optical loss, right? Or has a better passivation effect. I think all of those are very important in terms of for the metallization paste development to enable high efficiencies from the front side. And one of the another might be sometimes overlooked a little bit is for the front side is the bulk resistivity of the fingers, and I think that's becoming more important for the front side aluminum silver paste as we are driving toward final line printing, because the addition of the aluminum actually has a negative effect on the finger resistivity. So those are some of the considerations that we have to take into account when we are designing the aluminum silver paste for the front side. And for the from the backside silver paste, a lot of it is in terms of how to ensure a very high throughput, in terms of very high yield. So the paste design has to be able to withstand a very good green strength, so it can be printed on without the lines falling off. And as well as there are some good opportunities to reduce the silver content or the laydown from the backside. And of course, that has to take into consideration of the bifacial requirements for the N-TOPCon. There are screen designs that, the tricks that we can play to reduce laydown, but of course, overall, it has to be balanced. And a very hot topic is how to make sure the metallization paste on the backside could result in to maintain the passivation quality of the TOPCon contact, and also enable thinner polysilicons. That has a very good big impact in terms of both on the throughput with a thinner polysilicon, as well as a potential gain on the efficiency from the reduced parasitic absorptions in the polysilicon. So I think there's still a lot of work done on the backside, even though for the backside, we can leverage a lot of the learnings as well as the experiences that were gained from the silver paste development for PERC SE. But I think there are still a lot of in terms of optimizations or customizations that's required to really have a very good performing paste that's very compatible with the TOPCon structure. And another topic that from the backside is that may become important is the texture, which I will allude to a little bit later. And overall, the backside and the front side has to also ensure to have a very good compatible internal co-firing, right? So that so that you could have both the front side and the backside, both the recombination as well as the contact resistance be optimized simultaneously. And over here, I also throw in the bus bar. I think that's a exciting opportunity to reduce the laydown. So for the bus bar, we could, if we can do, and that's already been demonstrated now in the P-type PERC technology by the adoption of the dual printing. And I think same strategy could be adopted for N-TOPCon to reduce the laydown on the bus bar. But then, of course, that has some requirements on the bus bar development to make sure the bus bar could withstand a good adhesion, as well as a processing window and reliability that's required with a low laydown. But I think that's in large part being solved for the PERC SE, and it's more of just adoption into the N-TOPCon. Okay, so before I jump into the more of the technical details in terms of the technical challenges for the metallization. So just kind of give a little overview of some of the more of a higher level challenge and then our approach from Solamet in terms of how do we develop our products to meet the needs. So as mentioned earlier, so one of the things is with the metallization technology in this stage, that is true for both the PERC as well as for the N-type technologies. It's that the complexity, even though the technology is getting more refined, but then there are small changes in the processing of the solar cells. For here, example, in the cycle, I kind of drew up some of the key processing steps for the N-TOPCon. And the challenge here for the metallization is every single step matters in terms of the paste design. For example, the texture, and we talk a lot about the polysilicon deposition process, which could affect the crystallinity of the polysilicon, the density, which will in turn affect the chemistry of the during the firing, right, as well as the printing and screen design. So all of this has a profound impact on the paste requirement. So it really requires a lot of a close collaboration between the cell maker as well as the paste maker to really develop and customize the paste to optimize the process, the performance together. And so one of to enable that, and one of the needs that is required is the ability to do rapid product customization. So at Solamet, what we employ is more of a toolbox concept for rapid customization. So we have for the paste, we have three main classes of ingredients. So the organic vehicle, the metal, and then the glass fit. And so what we develop is then we have the expert teams that develop the tools, we call so-called tools, for example, the different organic vehicles that are customized to give the printing performance of different type of screen designs. Sorry, to give on the screen designs that, that could be optimized to give the best internal printing performance as well as laydown performance. Right, and then the metal particles, and then most important in the glass fits, because that has the most profound impact in terms of the recombination and contact performance, right? And so that be able to develop different type of glass fit chemistry for both the aluminum silver paste as well as to build on the natural oxide chemistry for the backside silver paste. I think it's a very important in terms of being able to do rapid customizations for the N-TOPCon product development. So now a little bit more detail in terms of the technology development. So here I'm going to just kind of highlight some of the key advancements that we've, as well as some of the understandings that we have made at Solamet. And I think we have the tools that's ready to work with the customers to be able to develop some of the improve and better products that's for the efficiency as well as to reduce the cost. So here, first highlight is on the development of our fine line vehicle technology. So through the what we found through our studies in the finance in the printing vehicle technology, I think what we came to a learning is that the vehicles is for different screen designs, especially if we consider like a conventional or mesh cross screens. It requires a different type of rheological properties. For example, like the slip or the viscosity or the yield of the paste. And so based on those fundamental understanding, then we can develop different type of vehicles that could be customized for the screen the customers are using, or even like for the so here are the examples we show the some of the actually these are the early examples that we show for the some of the fine line screens that we're able to use our paste to print that. And then we also, so on the right, we use a graded finger openings that goes from 12 micron to 20 micron screen openings. And we use that to kind of study the printability of our paste and, as well as on the different screen designs. So the top example is more of a standard, kind of standard design with a thicker mesh. And then we can also, be able to customize our vehicles to develop a very nice printable paste that can, be able to show very good a continuous continuity in the line down even to like 12 to 14 microns at the very narrow with thinner mesh or thinner emulsion designs. And that's, I think, is very important in terms of being able to reduce the laydown by, using the thinner screens. So, and then in the end, it also has to, make sure to be able to customize the vehicle to provide excellent long-term printability as well as the morphology and aspect ratio that's required for electrical performance. So I think, and to demonstrate that, here I show some of the results from from our demonstrations for our vehicle the innovations in our vehicle technology for the P-type PERC. So here are the two examples on the top. The two examples that we're able to use our improved vehicle technology to in the first case is to couple it with a screen optimization to deliver a very significant efficiency gain by by using a fine line screen. Of course, this was a little early example where the screen opening for the standard screen for the standard mesh is still at 22 micron, and with the MCF we're able to deliver over 0.15 or 2.2 efficiency gain by being able to couple it with a screen design, being able to by maintaining the laydown. Now, if it's more cost sensitive, then we can also by using a thinner type of mesh design with a different type of vehicle, and we're able to maintain the efficiency, and in the second example here to deliver like over about 15% savings in terms of laydown, and that's very substantial for a metallization for a P-type metallization. So then the question is, then how can we adopt this great advancements in the metallization for the fine line printing especially for mesh cross-free to N-TOPCon. And I think there are a few challenges that I just want to discuss about. So one is the vehicle has to be customized. You can build on the rheological understandings that have been developed for the P-type, but the vehicle has to be customized because of the differences in the inorganics, especially in the aluminum and the glass fit, and that will require a different type of a new dispersion improvements to ensure that it maintains a good fine line as well as a long-term printability. Now, the other challenge I think as we drive to fine line is a finger resistivity of the aluminum silver paste. So the aluminum is a key ingredient in I'll talk about a bit more later, it's in the aluminum silver paste to enable a low resistance ohmic contact, but it also has a severe impact on the resistivity of the fire finger. And that's because the aluminum itself has a, it inhibits the densification of the silver. So the resistivity actually increases quite substantially with the addition of the aluminum. So that may have an impact on the resistive loss in the finger. But of course, some screen designs, for example, you can couple it with the SMBB that was mentioned earlier, that may be able to reduce the resistive loss. But I think there's opportunities, but we see that maybe a bottleneck there. And so that means there is a requirement for new innovations in terms of metallization paste chemistry to enable a higher conductive finger for the front side. Okay. So the next topic, I'm going to talk about the recombination challenge for the N-TOPCon for the aluminum silver paste, and that has been, this is actually a old topic, for M-perc has been studied quite extensively when the M-perc was for M-perc, and so on the middle picture, I kind of show a SEM image from one of our from the cross section from one of the front side aluminum silver metallization. So one of the key topics that has been discussed a lot in the metallization as well as in literature is we always talk about the aluminum silver spikes, and that has a negative impact in terms of on the recombination, especially if we are worried about moving to shallower junctions, right? We might be worried about shunting the junction through the aluminum silver spikes. So there are a lot of chemistry that we can do to control the size of the aluminum, to control the size of the spike, as well as to kind of mitigate that issue. But one of the often overlooked issue in terms of recombination is actually from the glass frit. So the glass frit itself, actually from the example here, in the model example here I show on the experiment I show on the right side, is where we did a study, a PL, a simple study on one of our commercial, earlier generation of our commercial aluminum silver paste, but just removing the aluminum powder, and then just fire the print it and fire the paste on a N-type, on the M-perc wafer. And what we found is that the glass frit itself actually could, we even thought could actually induce a severe recombination. And that is actually coming, if we do a more detailed study, we can actually, what we found is actually the glass frit actually etches the passivation layer, especially near the peaks of the pyramids, and that actually has a very severe impact on the recombination. So what we focus on in the past year is would be developing new glass frits chemistries that is compatible with the aluminum silver paste and be able to significantly reduce the recombination, and that's the example shown on the bottom, while still being able to maintain the recombination, the contact resistance at 1.5 milliohm centimeter squares or less. Now, of course, there is a lot of ongoing work by the cell makers in terms of optimizing the AR coatings, the design of the passivation stack. So that will be more work in terms of required to further optimize the glass frit in terms of to better match with the new designs to ensure that we be able to obtain a low recombination. A low recombination, a paste, as well as be able to maintain the resistivities. So why can we move away from the aluminum, right? So that has been also a topic, and we actually in Solamet we delve into that very deeply in terms of both developing aluminum-free solutions, as well as understanding the mechanism in terms of what is the role of aluminum in the aluminum silver paste. So here is another a model experiment we done from the team, from the Solamet team back a few years ago, and we looked at the role of the aluminum in the aluminum silver paste. And so here we use a model experiment. Our model experiment was basically built on a polished boron wafer, so without the passivation layer, and then we printed a fritless aluminum silver paste to exclude the impact from the glass frit, and then just look at the reactivity between the silver and then with the silver paste with the wafer, as well as the role of addition of aluminum into the silver paste. And then So what we found is, even without the glass rate, what we found then from this study is that, with the presence of aluminum, it actually catalyzed the formation of this aluminum spikes, which are then the contact points that we often observe, right, in the typical aluminum silver paste. So that's why aluminum is a critical ingredient for low resistivity contacts, especially to be able to form those contact points or the spikes, or over here even the small, basically the silver precipitations into the silicon. So that means during the firing process, it's very important to make sure that there is a physical contact between the aluminum and silicon to initiate that formation of the silver contacts. But then, as mentioned earlier, the aluminum has a negative impact on the resistivity. So there is there is still requirement to balance the amount of aluminum, which means the contact points, as well as the glass rate chemistry, to ensure we minimize the amount of aluminum that's in the paste, so that to ensure that we're able to leverage as much of the finite printing technology as possible. So here is just kind of summarize some of the key design points for the aluminum silver paste, which I think we have made a great stride in terms of improvements, but I think there's still a lot of room for further improvements. And I think we are very just for some demonstrations here, we have actually tested both of the new concepts internally as well as externally, and being able to demonstrate over 0.1% efficiencies versus the current baseline. So I think there's still, with the closer collaboration with the cell maker, I think there's still a lot of room for further efficiency improvements, especially considering the optimizations of the emitter design as well as the ARC coatings. Okay, now the next challenge for the N-TOPCon is the rear side, the rear side silver paste. So as mentioned earlier, currently the rear side silver paste is basically leveraged pretty much from the metallization paste for the silver paste for the PERC, and but then of course it has to be customized to match with the current processing technologies for the TOPCon, especially considering the previously the speakers has talked about the different deposition processes for the polysilicon, right? So the metallization paste has to be able to be optimized, right, to work with those different processing technologies. So when we're studying the metallization, one of the roles we're trying to understand is what is causing the recombination. So recombination of the in the rear side. So what we found is actually very interesting in our experiment is if we put a typical PERC paste, a P-type paste down. So what we found, if you intentionally overfire the metallization, so what we found is actually the issue is actually coming from the silver precipitation into the polysilicon, and the silver precipitation actually almost in this picture shown here almost self-stops right at the tunnel oxide. And so the issue, so the main challenge then, is how do we control the precipitation of the silver into the with the reactivity with the polysilicon, and that's what I alluded to earlier as as a different polysilicon technology, deposition technologies. It has an impact in terms of the structure, and the chemical property of the polysilicon. It will actually have a pretty severe impact in terms of the reactivity with the silver paste, and then enhance the precipitation of the silver. But from the paste side, we can from the chemistry side, we can improve on we can customize our free chemistry to work better. But I think one thing that was kind of interesting, that in some of the studies we did was we found that the texture could actually be a very cool, very interesting tool to supplement in terms of be able to control the recombination while maintaining a very good low contact resistivity. And I think this is also some old wisdom that have been studied during the day, back in the days on the development of P-type, where the texture has a severe impact for the etching of the passivation as well as the formation of the contacts, right? And that we can kind of understand that both from the fluid mechanics during the firing process as well as the three-dimensional etching process. And so I think there is a good opportunity in terms of leveraging that concept in terms of be able to optimize the texture along with the paste chemistry to be able to simultaneously minimize the recombination as well as still being able to maintain the excellent contact resistivity. And that's the example that's shown here through a study that we did by polishing the wafer a little bit, and then we'd be able to severely, it's very significantly reduce the voltage loss coming from the texture. I think that's something that be very interesting in working with some of the cell makers in terms of to look at the to look at the opportunities there to see if we can realize that opportunity.
Dr. Guo, you have 5 more minutes. Yeah.
Okay. Yeah, almost there. So so here is an example where we show the for our N-TOPCon, we're able to demonstrate from our new paste chemistry to deliver some improvements over the production baseline. And so for the next couple of slides, just kind of have a little discuss briefly about so what's next after TOPCon, right? So we see the TOPCon is from the very exciting news that it's coming into reality. So we're just kind of thinking ahead, what's next? I think the TOPCon itself, from the self engineering perspective, it's a very nice platform. I think the next logical step to move forward is the back contact. And so that basically just completely eliminates the shading loss of the metallization, and then and be able to really maximize the performance of the solar cells. Of course, for the back contact, the quality of the wafer is a key driver, right? So, but with the increasingly higher quality wafers, I think both the N and P type back contact TBC may become a reality, and it actually has already been demonstrated, by the different research groups. So just a few words on the metallization for the back contact. I think there are two approaches that we can go. So one is based on a non-fire through. So that's basically leveraging the very mature laser contact opening technology, LCO technology, right? So we can use laser to open the contacts, and then we can do screen printable technology like one of the Solamet products that we developed for IBC, or we can imagine different type of other low temperature metallization technologies that could provide excellent recombination while and the contact performance. And then the other approach is more of adopting the current high temperature fire through technology, the metallization. We can also basically the technology that had developed from both N and P type. So for the back contact, the one exciting aspect of it is I think by removing the constraint from the front side shading, by moving I think it opens up more opportunities and then the options for the cost-effective metallization, especially considering the use of for example like aluminum paste for the back for some of the to contact certain regions, and then that could actually bring the metallization cost down quite significantly. Okay, so to wrap up, so I think everyone on the forum agrees that N-TOPCon is very exciting and it's become a reality. And for the metallization perspective, it's still very challenging, but I think we see a great progress in terms of both in the cell processing as well as in the new understanding the metallization, the chemistry. I think we see there is a big opportunity for the metallization paste to contribute to realize higher cell efficiency and lower cost. And building on the TOPCon platform, I think TBC could be a very exciting next big thing. And to wrap it up, I think Solamet is very excited to be entering this new chapter. We're committed to continue to invest in innovations, and we are looking forward to, as a more agile, independent company, we are looking forward to collaborations. Thank you.
Thanks a lot. That was very in-depth and great information about metallization for TOPCon. It was great to have you. I think there are quite some questions in the chat. It would be nice if you could answer them there. We have